you're still going to see an increase in bile with lipid and acidic food content because the secretin is going to make the liver make more bile at that time. And then, yes?
Where are the bile salts going?
Where's the what?
Bile salts?
The bile salts are going through the common bile duct, through the hepatopancreatic ocula, and into the small intestine. They're going into the duodenum.
So why do people say, like, oh, there's bile in your stomach? Is that just some weird slang thing?
Yeah, well, you can throw up bile, so if you throw up, it's going to be stomach contents. If you throw up extensively, you're going to start to see a greenish color to that, and that's you're throwing up from your small intestine.
Oh, cool.
I'm going to try to do that when I get home. Alcohol induced.
Also with diarrhea, on the opposite end, so first of all, it's just the fecal matter, but then extensive diarrhea, you start getting small intestinal contents, and you start to see the yellow-greenish color of the bile as well, which is not, the bilirubin is coloring the fecal matter a yellow-brown, but as you have more and more liquid fecal matter, it starts to look more greenish from the liver part. So secretin also binds to cells in the pancreas, but here it increases the amount of bicarbonate ions. Okay. So some form of that, I'll have the diagram already drawn. I've learned not to let you guys draw pictures. But I'll have a similar diagram for that, asking you to tell me, where does this have an effect? Does it have a positive or a negative? Does it inhibit or does it stimulate the activity or the release of that particular organ's components? Yes, ma'am.
Never mind.
Okay. Okay, I'm going to erase that board in just a moment, so... Yes, sir.
I got a small issue. What's the S line mean?
Small intestine.
Okay.
Duodenum, if you will, but it's small intestine. So I'm just giving the source. In other words, it's the presence of lipids in the chyme that causes the small intestine to make cholecystokinin. So that's going to be an excitatory cause action on the small intestine.
Professor. So you
Yes.
said increase in acid produces secretin, is that what you said?
Yes.
Okay.
So, and I have lipids, it's actually both protein and lipids for this. And then the acid is on the secretin. That makes sense because the bicarbonates are going to neutralize that acid. Okay, so now let's look at the small intestine, specifically the jejunum. It's where most of our digestion takes place. So we've mixed all this material in the duodenum. And now as this moves into the jejunum, we start to have the digestion and the absorption. So most of that digestion takes place in the jejunum and the early part of the ileum, and then the rest of the ileum we do some absorption. Okay? So this looks very complicated. You actually know everything that's on that diagram right now because of what we covered. Yes, you do. Because we covered it when we did the kidneys. Oh, well, okay. All right, I'll rephrase it. You are familiar with everything that's on the board, okay? May I erase the, oh, you're almost, still taking a picture, Caroline, sorry. Okay? So now we have this mixture occurring. We'll look at carbohydrate digestion first. So the intermediate step, so we're in the small intestine.
Jejunum section, right?
Yes. And we're assuming that not much has happened with carbohydrates, we don't have to assume, in the mouth, and nothing happened in the stomach, all right? So our polysaccharides, within the lumen small intestine are going to be acted on now by pancreatic lipase. And what hormone would increase the amount of pancreatic lipase? From the previous material I had on the board? Pancreatic lipase, gastrin's going to work on gastric lipase. So pancreatic lipase, yes, cholecystokinin. It increases pancreatic digestive enzymes. So pancreatic lipase, I'm sorry, amylase is what I meant. Amylase.
Yeah, that's.
Sorry about that.
That's all it's kind of.
Yeah, no. Polysaccharides, pancreatic amylase, and so our products are going to be sucrose, maltose, and lactose, as we went over early on in class. That's what's in the lumen of the jejunum. So looking at our diagram here, what this diagram is illustrating is the apical surface of the simple columnar cells covering our villus. So this is a simple columnar cell. On a villus. Of the small intestine. Right? So this is now in the lumen, too big to cross the plasma membrane and move into our cell. But remember, the small intestine makes the final digestive enzymes. So rather than secrete them into the lumen of the small intestine, these are found embedded in the membrane of the small intestine. So just for example, this would be sucrase. So the small intestinal columnar cell made sucrase. Rather than dumping it into the lumen of the small intestine, it just embeds itself in the plasma membrane on the microvilli. So the more microvilli we have, the more enzymes we have, as well as the more surface for absorption. In conjunction with that enzyme, we have a secondary transport molecule. So how did this work? Well, I'll get to it in just a moment. Sucrase is going to interact with sucrose, and we're going to see two molecules, one of sucrose, one of fructose. And secondary transport
You want a glucose one or fructose?
is going to send a glucose or fructose into the cell. So it is digested, its final stage of digestion is occurring right there at the membrane, and then it's driven into the cell along with sodium via secondary transport, just like we talked about in how glucose was removed from the filtrate of the proximal convoluted tubule. So what would you expect at the bottom of the cell? A bunch of sodium-potassium pumps, creating a sink, increasing the drive of sodium into the cell. Okay? So this complicated looking diagram is showing the microvilli, and an enzyme for lactose, an enzyme for maltose, and an enzyme for sucrose. And there's a secondary transport for the simple sugars. And then again, the same as in the proximal convoluted tubule, they leave the cell via facilitated diffusion and move into the blood capillaries of our villi. So was it familiar? Please say yes.
Yes.
Thank you. Yes.
On the picture, the monosaccharides are broken down after it went down, but over here you have already broken down.
Okay, so they're actually broken down here at the surface. This is just showing two different monosaccharides are entering the cell. They're not broken down in the cell. They're broken here in contact with that enzyme. So that reaction is still taking place in the lumen, but at the membrane, and then once they're broken down, they're just saying it comes into the cell, not the breakdown occurs in the
They
cell.
don't actually cross the membrane until they're broken.
Right, so they cannot cross the membrane as a disaccharide.
It's either or of those based on the sucrase, maltase, lactase. It's like the guy that says, hey, who are you?
Yeah, so the sucrase will only measure, recognize the sucrose. And then that breakdown occurs actually, like I've drawn it out here, and then each individual monosaccharide would come in with sodium.
Both of them.
Okay, so they all come in at the same time with sodium.
Yeah, well, I mean, it's usually one at a time.
Well, but, okay.
Yeah. Okay? So that aspect of moving glucose or fructose or galactose from the lumen of the small intestine across the columnar cell into the blood is the same mechanism that we showed in the kidney occurring at the proximal convoluted tubule, creating a sink with sodium potassium active transport pumps, and then secondary transport using symport channels moving the simple sugars into the cell. Okay, the same type of movement into the cell occurs with proteins. So in the small intestine, we have, again, a little bit of protein digestion occurred in the stomach, but an insignificant amount for our overall body. So for proteins now, we have polypeptides. And in the lumen of the stomach, in the lumen of the small intestine, this is mixed. Our pepsin no longer works, right? It only works at an acidic pH.
So now you're gonna have the amino.
So now we have the bicarbs again are elevating the pH, and so we're going to have not quite the aminopeptidases yet. We're going to have trypsin, chymotrypsin, and those are going to be creating small proteins. Okay, so peptides and oligopeptides.
Those are hormones. Those are enzymes, correct?
Okay.
And those enzymes?
Enzymes?
These are the enzymes, yes. So these are pancreatic enzymes, but working in the small intestine. All right? And let's look at some images here. So this is our protein. We don't have any enzymes that work on this in the mouth. In the stomach, we have pepsin. And so pepsin is going to break down our large protein into smaller peptides, oligopeptides, but still not small enough to pass across into the cell and then into the body. So we're left with that. Then we move into the small intestine, that should be an O there instead of a Y, and we do the same thing, but with pancreatic enzymes. Because the stomach enzymes, pepsin, works at an acidic pH. And we don't have an acidic pH in the small intestine. I don't know why our body needs to change the pH. Why do we need to stop? Why do we have to be so acidic? Why do we have to stop that pH? Why can't it be standard all the way through? I don't know. But we bring our smaller proteins into the small intestine, and we continue to work on the large proteins, but now with pancreatic enzymes, trypsin and chymotrypsin, and break those down into smaller peptides.
Is it because it would denature the proteins?
Well, why don't we just have an alkaline pH in the stomach? I mean, most of the digestion of the stomach is mechanical anyway. So it seems to keep starting and stopping and starting and stopping and creating. It's like reinventing the wheel every time. All right, so now that we're in the small intestine, the enzymes that are found within the membrane are carboxypeptidase, and aminopeptidase, and I'm not trying to imply that they're only one on each microvillus. Okay, they're all going to be all over the microvilli. And dipeptidase. So it's kind of cool how they work. The carboxypeptidase works on the carboxylate. So where we find the acid of our amino acid. And it will cleave off one amino acid at a time, but only from the carboxylate. And then when we look at our aminopeptidase, it does the same thing, but only one amino acid at a time at the nitrogen end. So we're kind of shortening, cutting off our rope 1 inch at a time, but from both ends, and it's getting shorter and shorter from both ends. And finally we end up with 2 amino acids. So which will we use? The carboxypeptidase or the aminopeptidase? Well, we put in the dipeptidase. And that splits our final pair of amino acids. And now those amino acids are transported into the cell, just again like the proximal convoluted tubule, with symport of sodium ions. Secondary active transport with the symport of sodium ions. And I have this drawn out for you in your lecture notes. All right. So this is just showing that illustration as it was a different textbook, so the picture is slightly different, but the same event is occurring. The enzymes are still bound in the microvilli. Okay, lipids are not a 2-enzyme, they're not a 2-stage, at least triglycerides are not a 2-stage step. We don't have an intermediate step and a final digestive stage. For a more simple type of digestion, it actually takes longer. Which is why if you're trying to lose weight, rather than not eat any fats at all, you're encouraged to eat healthy fats, olive oil, avocados, and so on, because in addition to the vitamins and nutrients that they have, they stay in your digestive tract longer and help you feel less hungry, all right, so that you're not just passing that through. They hang around a little bit longer because it takes longer for digestion. So I'm going to draw this image sideways. So, columnar cell, microvilli. This would be the lumen of the small intestine. So we have lipid droplets.
Are we still in the dream?
Huh?
Are we still in the dream?
Yes. This actually goes on to the ileum because it takes so long for lipids to be digested. So with the mechanical churning going on in the stomach, we have taken a large fat globule and broken it down into smaller lipid droplets. Here's where the biosalts come in. So attached to the lipid droplets, we have our biosalts. And when we do, I'll talk, this creates a structure known as a micelle. So the lipid, the next slide, I will come back to this one, the next slide kind of illustrates these micelles. And so the bile salt is a fat-soluble material that has charges this is non-charged. So the non-charged region interacts with the oil, the lipid, and the charged region then repels the other bile salts of like charges. It's like trying to put the same ends of two magnets together. They're both positive or they're both negative.